Hello and welcome to another video lesson with Takoa Lawson. We're still working on the introduction to AP Physics, and today we're going to start looking at significant figures. You should have already watched a video about the big ideas and the nature of science. This next lesson will be all about significant figures, a little bit about uncertainty and why they exist, and then we'll be closed with just a little bit of some of the strange rules that we have to know about significant figures. So this lesson's all about significant figures. Significant figures are really important when we make measurements. It's really about when we use tools that significant figures become important, but they'll be used in a lot of science classes, especially when you get into college level, which this happens to be an introduction to. Usually it's most important when you're dealing with measurements in labs or when you're dealing with calculations that use measurements. The definition of the significant figures, it's a little bit, you'd think every figure is significant, and of course it is. Every figure has meaning. Every value or every digit has meaning. However, they're not all significant figures, and that'll make more sense hopefully by the end of this lesson. So we're going to talk about the importance of the values in a measurement, and we're going to be able to eventually be able to identify what's the difference between a significant figure and an insignificant figure. Although the term insignificant figure is not really correct, just how many significant figures there are in a value or a measurement. So why do we even have significant figures? Significant figures are really the product of the fact that we use tools to make measurements. So as soon as we started needing tools to make measurements, at some point we figured out that since the tools we use are not all the same, it's important to be careful, and that's when the concept of significant figures started to gain traction and become more common dealing with measurements. Where it all comes from is the fact that using instruments, which is great, actually inherently has some problems. No instrument is perfect. Instruments have some kind of flaw. Every time you try and make a measurement, it's impossible for it to make a perfect measurement. So because our instruments have some errors or some inaccuracies in their design, it's important for us to be careful about the numbers we report making measurements with them. Those numbers have to make sure that they don't show greater precision or they don't go out beyond what's capable of the instrument. And again, right now that probably sounds pretty confusing, but it'll make sense when you start to see examples and as we go through the lesson. In addition to the tool being important, the scientist is very important. The person making the measurement also plays a role, and it's important they use care and skill, and we'll talk about some of the things that you have to do to avoid errors when making measurements using instruments. Here's an example of just such an instrument. This is a triple beam balance. A triple beam balance is used to measure mass. If you wanted to use this to measure mass, you would place your mass on this surface, known as the pan, and then you would move these riders that are over here along their individual tracks until you're able to get it so it balanced, so that this pointer on this side is pointing at 0. You can see right now it's pointing at 0 without anything on it because it's measuring 0 mass. All the riders are all the way to the left. But if it was balanced and the riders were moved to the right some amount, you would add up the numbers of the masses for each of those tracks or each of those different riders, and that would give you the total mass that must be sitting on the pan, or at least the mass that this scale is measuring. Another common instrument that you've probably seen before is the graduated cylinder. The graduated cylinder is a very important instrument for measuring volume. So we pour the liquid in, and then we look and we see where the bottom of the meniscus is, and from that we're able to tell the volume of the liquid inside of the graduated cylinder, if we're measuring it for density or if we're going to use it and then we just want to make sure we have the right amount. One of the things about graduated cylinders and rulers and sliders and any of these different instruments, especially if you're reading tick marks off of a scale, you have to be careful about a very common error that's referred to as parallax error. Parallax error occurs when your eye is not aligned with the tick mark. If we were going to measure the volume of liquid in this graduated cylinder, we'd want to carefully line up our eye so that it was along a normal or 90-degree line with the bottom of the meniscus. By placing our eye at exactly that location, when we are looking at it, we're able to make sure that we're looking at it from a 90-degree angle and we don't get a parallax effect. The parallax effect is where you're either too high above or too far below. And it actually turns out, and you can see this pretty easily if you put your pencil next to a ruler and you slide your head off of that 90-degree line and you move it, and you'll notice that the pencil seems to grow and shrink a little bit up against the ruler. But in fact, its length's not changing, it's just your line of sight is. So it's really important when we're reading tick marks, you want to be at 90 degrees. So that's why you'll see people put things down on lab tables so they're flat, so we don't see any effects of the liquid being pulled by gravity, and then leaning down and making it so that their eye is perfectly level with that meniscus to be able to get an accurate reading. Let's look at some examples of using different instruments and see how they can actually give us different measurements. First, we're going to look at the following meter stick. If you look at this meter stick, you'll notice it's simply a plank of wood that's exactly 1 meter long. Most of the times when looking at a meter stick, you notice many smaller lines. You notice many tick marks that break it into smaller pieces of length. In this case, there are no smaller pieces of length. It simply identifies where 0 is and where 1 meter is. That means this instrument would work well if we're trying to measure something that was 1 meter or an exact number of meters long, because it'd be relatively easy. But in this case, we're going to try and measure a pencil. When we look at this pencil up against the meter stick, clearly it's not 0 because it takes up some of the length, but clearly it's not anywhere close to a meter either. So the question is, how would we use this meter stick to give a correct or precise measurement about this pencil's length? There's a lot of different strategies we might use. So one is you'd say, well, clearly it's not a meter. You might imagine how many of these pencils, if I took this length, how many times would I be able to fit that? So I could probably take 1, 2, 3, 4, 5, 6, 7 and some change, but that's not a very precise measurement, not a very good measurement to report. Another strategy we might use is to say, okay, well, if this full thing is 1 meter, then we could break it in half, and that would be about half a meter. And then we could break that half in half, and that would be about a quarter meter. And we'd see, okay, well, it's definitely less than a quarter meter. Well, if I were to try and take that quarter meter, I'd say, okay, well, that's definitely more than 10 centimeters. If the quarter meter is 25 centimeters, it's more than 10, but less than 20. So now I have a reasonable estimate that it's more than 10 centimeters and less than 20 centimeters. But I can't say 11.832 centimeters, because that would suggest I was certain that what is 11.832 centimeters. And I don't know that. I'm guesstimating that it's probably more than 0.1 meters or 10 centimeters and probably less than 0.2 meters or 20 centimeters. I don't have any smaller tick marks. I can only estimate to the best of my ability to those tenths. That would be me estimating one place out. I know for sure 1 meter. 1 meter ends at the decimal point. So the next place is the tenths. So I can estimate tenths. So the question is, using this meter stick, would I estimate 0.1 meters or 0.2 meters? That's really my only options. To me, it looks like it's definitely closer to 0.1 meters than it is to 0.2 meters. So my estimate for this length would be that it's 0.1 meters in length using that instrument. Fortunately, there are other instruments out there. Now let's imagine doing the exact same process, but this time our meter stick is going to have actual tick marks in between it. Now again, this doesn't necessarily resemble the meter sticks you're used to seeing. This meter stick still shows 0 and 1 meters, but what's happened is every 10 centimeters or every 1/10 of a meter, it's got a tick mark. So now we know for certain if something is more than 10 or less than 20, more than 40 or less than 50. And our estimate before that this pencil was more than 10 and less than 20 was a reasonable estimate. We can see now with these tick marks, it's definitely more than 10 centimeters and it's definitely less than 20 centimeters. However, we run into the same problem we had before. We don't see any smaller marks. Now, 10 centimeters would be 0.1 meters. So I know for certain it's 0.1 meters and it's less than 0.2 meters. So as a scientist, I get to estimate what that next point is. And this is where that skill of the measurer comes in. The better you are at kind of breaking it up, whether you want to kind of divide it out visually, or whether or not you're giving yourself some kind of landmarks, or how you're doing it, as long as you're looking at a 90-degree angle, is really up to you. And that's why some people might have a slightly different estimate for that last place value, just based on what they decided to use, or what. When I look at this, it looks like it's about halfway between them. So that would be about half of a tenth, or about 5/100ths of a meter. So I would say, okay, well, this is about 0.15 meters. Or if we wanted to say it in centimeters, since it's between 10 and 20, halfway between 10 and 20 would be 15. So we'd say 15 centimeters. And I would say, using this, I'd get 0.15 meters. And what we see now is with those smaller tick marks, we're able to get more values. We know for certain it's 0.1, and now we're estimating the 5/100ths. Before, we didn't know for certain the 0.1, so that was our estimation. Now for the last measuring tool, we're going to use a meter stick that's a little bit more familiar, and in this case, we've got it marked down to the individual centimeters. This shows the 1/100th of a meter, 1 centimeter. So there's 100 individual marks that end up covering up the whole meter. Now I can see very clearly that this pencil that we've been looking at is more than 10, more than 11, more than 12, more than 13, more than 14, but not 15. So it's definitely 0.14 something. It's 0.14 meters, or 14 point something centimeters. Now when I try and estimate there and try and give it a careful look from directly above, it looks like it's about halfway between the 14th and the 15th centimeter mark. What would I estimate as halfway between? And that'd be 14.5 centimeters. Or if we're going to describe it in meters, I know for sure it's 0.014 meters. And now that next estimated place is going to be the hundredths. So I estimate that it's halfway between. That's how I get 0.145 meters as the measure of this pencil using the third meter stick. When we talk about these three different meter sticks, they're clearly different from each other. Mainly, what you'd say is, well, obviously, some of them have tick marks that are smaller, some of them allow you to see smaller lengths on them, and that's absolutely true. What really is happening is that if you compared our measurements using them, our estimated place value is changing. On the first meter stick, we estimated the tenths place. On the second meter stick, we estimated the hundredths place. And on the third meter stick, we estimated the thousandths place. So not only are they different by the tick marks, but they're actually different in where our estimation is. And what you should notice from that is our estimation is actually getting a smaller and smaller place value, or estimating smaller and smaller increments of length, which gives us an idea that we're probably getting closer and closer to the true or correct value for that pencil. Now, precision, which is often used in science when you say something's precise, we're not necessarily saying it's the true value. We'd like it to be, but that's a little bit different. That's about accuracy. If you're saying something is the true value, you're saying, oh, that's accurate measurement. When we say precision, what we're really saying is that if different people use the same instrument, they would get the same result or very similar results. Now, if we compared the first meter stick, it's less likely that three different people making measurements would come up with the same measurement because there's no smaller tick marks. However, with the third meter stick, it becomes very likely that no matter how many people use it, they're all going to get very similar measurements because the precision is very high. The estimated value is a very small length compared to the length of the pencil. The question comes up, which meter stick was more precise? The meter stick that measured the pencil as 0.15 meters, or the meter stick that measured it as 0.145 meters? And the answer should be obvious. It's the meter stick that gave you 0.145 meters. We were certain it was more than 14 and less than 15 centimeters. While on the first meter stick, we were certain that it was more than 0 and less than 1 meter, but we were really estimating whether it was 0.1 or 0.2, and we kind of went with our gut that it was 0.1, but it could have been closer to 0.2, and then we would have been off, but we had no clues until we used some of those other measuring devices. When these measurements are made, there's a certain amount of uncertainty that goes along with the instrument. That uncertainty is important, and it's important that our measurements show uncertainty to the correct amount. So since when we report our values, when you tell somebody, oh yeah, I measured the length of the pencil, it was 0.145 meters, they didn't get to see you measure it. They don't know which meter stick you used. They don't have any idea about what the level of precision of your instrument was. So it turns out how you tell them the number, if they're scientists and understand the principle of significant figures, will actually report to them what level of precision your instrument had, or whether or not you had tick marks at the 10th place or the 100th place or not at all. When we look at the three values we got, which were 0.1 meters, 0.15 meters, and 0.145 meters, there's some uncertainty. What the general rule is, the uncertainty is plus or minus 1 of the smallest values in the measurement. There are some other rules that we can do for uncertainty. If any of you have been taking statistics or done any research, then you know about error bars and you know about z-scores and what you would do to be able to capture the true value in a certain reasonable estimate. That's really what we're doing here. We're saying that the true value is close to what we're measuring, but there's uncertainty in terms of our skill. There's uncertainty in terms of the precision of the instrument, because all instruments have some error in their design. So what we do is we look at the value, and in this case, the first one, which was 0.1 meters, that would be plus or minus 0.1, because that was our estimated value. So it could be off by a tenth. So it could be as high as 0.2 meters or as low as 0 meters. Now the 0 meters is a little bit weird. It just happens to be because we're close enough to 0. But what we're really saying is that the true value is between 0 and 0.2. And as if we all looked and we asked somebody to be able to look at that pencil against that first meter stick and say, you know, without thinking about what the actual value is, could you say for certain that the value has to be between 0 and 0.2? I think most people would reasonably say yes. When we look at the second instrument, we estimated at the hundredths place, and that's how we got 0.15. And so that would mean it's plus or minus 0.01 meters. So that means it's between 0.016 and 0.014 meters. And again, if you looked at that and you said, okay, well, it's definitely more than 10 and it's definitely less than 20. And if somebody said, well, are you sure it's 15? You say, well, no, might be 14. Are you sure it's 15? No, could be 16. You're really saying it's kind of within plus or minus 1. And the truth is, if I say it's 0.15, then I get between 16 and 14. But if somebody else said 0.14, then they would get between 13 and 15. So where you claim the true value is somewhat depends. However, we should all be within a couple of tenths of each other. Nobody should be saying, oh, it's 0.12 or oh, it's 0.19 if we're using the instrument correctly. For our last measurement, which was 0.145, we see that the estimated place value is in the thousandths place. Now we're starting to get down to a really high level of precision. We're basically saying we're pretty confident within 1/1000th of a meter what the length is. And the reason we have that confidence is because our meter stick showed us down to a smaller degree with those tick marks. So now it could be anywhere between 0.144 and 0.146 meters. But what we still see is even when we start getting these smaller and smaller uncertainties, there still is some uncertainty. And when we compare these three numbers, if we were reporting these values to another scientist, how would they would know which one's got more certainty or which one is more precise is based on where the estimated value is. The smaller the estimated value, the more precise the number or the measurement. Along with uncertainty comes the process of determining the percent uncertainty. How much uncertainty is there? The smaller the percent uncertainty, the higher the level of precision. The percent uncertainty is actually very similar to percent error, which I'm sure you've seen at another point in your high school or even in middle school. It's a percent, so it's a ratio. It's just a ratio of your uncertainty to the value you measured. And it gives us some interesting results. So if we start comparing the three values we had before and start looking at the percent uncertainty, so let's do the percent uncertainty of A. Well, our uncertainty value was 0.1. And our measured value was 0.1. And when you divide a number by itself, you get 1. And when you multiply 1 by 100, you get 100% uncertainty. And that should kind of make sense, since it could be as little as 0. Clearly, we're not very confident. There's quite a bit of uncertainty in that value, and it really has to do with our measuring device. When we calculate the percent uncertainty for the meter stick B using the same method, we take the percent, or the amount of uncertainty, which in this case was in the hundredths place, and we divide it by the measurement we had, which was 0.15 meters, and then we multiply it by 100. And when we calculate that, we find out that it's 6.67%. Although we're going to find out later on why this is actually 7% uncertainty. For the final meter stick, when we measure the percent uncertainty for meter stick C, we take the estimated value, or uncertainty, which was in the thousandths of a meter, and we divide it by the measured value, which was 0.145 meters. Then we multiply that by 100, 0.6897%. And then later on we'll find out why, but that would be 0.7% uncertainty, which means our level of uncertainty is getting very small. We're within 1%, we have a 0.7% uncertainty, which means we're pretty confident that we've gotten close to capturing the true value of the pencil. One of the things that obviously students ask at this point is, well, if there's errors, then why even make the measurements? Well, you're still trying to get good measurements. It doesn't mean that just because you don't have 100% certainty because there's error in your measurement doesn't mean that you don't find the measurement useful. It doesn't mean that it can't serve as a tool to get a lot done. And especially when you get to those measurements where the uncertainty is very small, you have a very small percent uncertainty, then we're pretty confident that those are the true values, or very close to the true values for that measurement. But when we talk about errors, there's 3 main kinds of errors you want to be aware of. Some are easy to deal with, some are not. An error can come in a couple of different forms. Systematic errors are a situation where you're consistently measuring values that are too low, they're smaller than the true value. It could also be that they're too high, they're higher than the true value, but you are consistently falling on one side and not the other. Random errors kind of bounce around. Sometimes you're above, sometimes you're below, and they kind of end up not being as big of a deal, because if you're sometimes above and sometimes below, but you average all your measurements together, you end up kind of washing each other out. And then of course there's blunders or human error, which are a whole different problem. For systematic errors, in order to always measure above or below, there has to be some kind of error in either how you're using the instrument or the instrument itself. Most obvious ones would be going back to something like the triple beam balance. The triple beam balance, if you don't start at 0, if it hasn't been put at 0 before starting it, or if one of the riders wasn't all the way to the left when you adjust it or you calibrate it so it's back to 0, then everything you weigh will be off, and it'll either be too high or too low depending on whether you had a rider moved or whether it wasn't adjusted to 0. Another one would be something like the graduated cylinder. If you're consistently not looking at it from 90 degrees, you're looking at it from standing height or looking down upon it, then you'll consistently have that parallax error that looks like it's a correct volume, but it's actually going to be too high or too low. In that case, if you're above it looking down, when you look at that scale, you're going to actually believe that it's a lower volume than it truly is. So you'd end up consistently getting a lower volume measurement. Meter sticks would be another example. If some of the ruler was missing and you're treating that as 0, there's a length there that you're adding on that's not actually part of the measurement, so you're consistently getting a larger measurement than the true value. While if a ruler doesn't start at 0 but there's a little end piece, or if it's a meter stick that has a little metal cap on the end where it extends it, and then you're treating that as 0, you're actually using that gap that doesn't get counted as part of the tick marks, and so where your measurement isn't accounting for that length, so you're consistently below the true value. Those systematic errors are usually pretty easy to correct. One, if you notice the ruler, if you're careful about parallax error, it's all about the skill of the measure, and you can avoid those systematic errors, making sure you check your triple beam balance. Another way you can do it is calibration. So you can take something that's a known length and you can measure it and make sure that you're getting the true value before using it for other measurements. You can take a known mass and you can put it on the triple beam balance and make sure that it comes out to be the correct mass so that you know that there's not any systematic or any problems with how the device is operating. Random errors are a little bit harder to control, but since we can't really control when we're randomly a little bit above or randomly a little bit below, what we do to try and control for that is we average. So it's all about multiple measurements. No measurement should only be done once. And the truth is, even 3 times is kind of a small number, but at least with 3 times we can average as many times as you can do in a safe amount of time, or depending on what the project is, sometimes you have to make many more measurements. If you have an instrument that you're getting very high precision, you might only have to make a couple measurements, but averaging them makes it so that any random errors, since they're randomly above and below, will be averaged out and hopefully not have any significant effect and skew your data. Then there's blunders, human errors, where we make a mistake. If you notice it, one of the ways you notice it, you have this huge outlier, right? Everyone measures the length of a dollar bill, and one person's is way different than everyone else's. Dollar bills don't change. There was clearly a human error. There was a blunder on that measurement. You can either remove it, or you can redo it and make sure that it's more accurate. There are a lot of different instances where a human error can be identified because it creates a major outlier. Sometimes human errors are small, and then we might not notice them, and in that case they might not actually get caught or removed. But that's one of the reasons why in a lab you should always have someone else check your measurements. You should always have different lab partners doing the same measurement, using the same tools so that you can compare and see if there's any blunders or any human errors along the way. One of the ways that we report the error is percent error. So percent error gives us an idea of how accurate we were, how close to the true value we are. One of the things that's interesting is that in order to have a percent error, we have to know what the true value is. So if we know the length of a dollar bill, why are we measuring it? Well, sometimes it's to practice the skill of using measurement. Sometimes it's some other analysis where we pretty much know what the standard is and we're trying to verify or trying to repeat that and see if we get the same result. Hoping, like we said in a previous lesson, that science being reproducible or verifiable means that we will consistently get the same results no matter how or where we make the measurements. Our percent error is done by taking the measured value, what we get in the lab, and subtract from it the actual or accepted value or the true value or what is currently known to be the value. And then that difference, which is how far away from the true value we are, gets divided by the true value and be turned into a percent. So the percent uncertainty was how much uncertainty to the measurement. The percent error is how far away from the correct value are we as a percent of the actual value. It's very important to know the actual value is provided or is determined in a better method or something that we're more confident in, while the measured value is generally what you get in lab or what you get using an instrument. We'll do some percent error calculations. A lot of times you'll do them as part of your lab, but you should have done a bunch of chemistry and you should already be pretty comfortable with them. So we're not going to spend more time on them on this lesson. The last subtopic of this lesson is going to be actual significant figures, determining significant figures. Interestingly enough, we started off this lesson talking about significant figures. This whole lesson is about significant figures, and I've used the term talking about measurements with significant figures, but we haven't actually defined what a significant figure is. You might have some clues. Obviously, it has to do with making measurements, and obviously those 3 meter sticks that we were looking at had different significant figures, so it might be kind of obvious to you. But a significant figure, aka or also known as a significant digit to the measurement. The numbers that when you report give some idea about the tool that was used to make the measurement. Now, to identify significant figures is the first part. So first thing we have to be able to do to use significant figures is understand how to use tools, which hopefully you get that you always use the tick marks that are provided on the tool and you estimate one place beyond. And then we're going to be identifying the number of significant figures in these values. So when we're trying to identify significant figures, it's really about how many significant figures does a value have. One of the ways we know is by identifying the type of value it is. First, counts. A count is something where you have objects and you're literally counting them. So if I had students in the classroom and I started counting them, 1 student, 2 student, 3 student, and got to 29 students, that would be exactly 29 students. I'm not estimating. I didn't use a graduated cylinder. I didn't use a ruler. I didn't use anything to estimate the number of students. I was literally counting them. Counts have an infinite number of significant figures. When we talk about another relationship that has infinite significant figures, it's ratios. When we say how many inches there are in a foot, it's not approximately 12 inches in a foot. We don't take a foot and measure how many inches are in it. It's defined. 1 foot is exactly 12 inches. So since 1 foot is exactly equal to 12 inches, that relationship, that ratio is exact. And just like a count, essentially we're counting the number of inches in 1 foot, it has infinite significant figures. We don't write it out. We don't write 1 decimal point 0.00000 to infinity, because you literally can't, and 12 decimal point 0.000 to infinity, because you literally can't. You could do 12 decimal point 0 with the bar, but that would be unnecessary, because we know that ratios of defined values have infinite significant figures. Things like 100 centimeters in a meter, 1,000 milliliters in a liter, 60 seconds in a minute. That's an exact value. That's one of these defined relationships or ratios that has infinite significant figures. The last bullet point brings us full circle back to what we started this lesson at. It's talking about instruments and measurements, and that's where significant figures become important. A measured value has a certain number of significant figures, and it's not an approximate. There's an exact number of significant figures. We count the number of significant figures. We might make the measurement and we might make some estimates, but we count significant figures. So any value has a number of significant figures, and we need you to be able to identify how many significant figures there are in any value that's given or written or that you determine. How do you determine if something's a significant figure? Well, there's the easy answer, which is you hope there's no zeros. If there's no zeros, everything's significant. All non-zero digits, which is 1, 2, 3, 4, 5, 6, 7, 8, and 9, are significant no matter what. Then you know that's a significant value, that's a significant figure, that's a significant digit. So we look for numbers 1 through 9 and we count how many of them there are, and those are significant digits or significant figures. Obviously, there's only one number that's not between 1 and 9. 0. 0 is the annoying number, because 0 can be significant, cannot be significant, or sometimes is significant. It literally can be everything. Never, sometime, always. So how do we figure out which of the zeros we're dealing with? And the truth is, you can't just know unless you know these rules. So you have to memorize the rules for zeros, and then when you're looking at a value, you have to remember, if you see a 0, how to classify or identify the type of 0 it is, and then recall this rule and determine if it's a significant digit or if it increases the number of significant figures in the value. So let's start with the easy one. Leading zeros lead the number, or the furthest to the left, or come before any other numbers. Middle zeros are sandwich zeros, or come between two numbers. And trailing zeros are zeros to the right or after all of the other numbers. We're going to look closer at all of those. Leading zeros are the easy ones to deal with. Leading zeros, zeros that are to the left of the other numbers, are never significant. We never have to worry about leading zeros. So, leading zeros we like, leading zeros never significant. Sandwich zeros, middle zeros, we also like. If there's 4 zeros between two numbers, for instance, 10001 or 10,001, all of those zeros are sandwiched between the two ones. They're all middle zeros, so they're always significant. Leading never, middle always. The annoying zeros are the trailing zeros. These are the zeros that come after all the other numbers. For instance, 550. That's 550. That 0 is trailing or comes to the right or is following the other numbers. Another one would be 0.150. 150 thousandths. That 0.15, those are leading numbers, so that 0 is a trailing 0. It comes after the last number. The difference between 550 and 0.150 is that in one case, there's a decimal place we can see or it's visible, and in the other case there isn't. So trailing zeros, or zeros that come at the end of the number, are significant if there's a visible decimal point. They're not significant if there's not a visible decimal point. Let's look at a couple of examples. I'm going to write down a series of numbers, and from those numbers you should do two things. One is determine if there's zeros, whether it's a leading zero, a middle zero, or a trailing zero. Then once you know it's a leading, middle, or trailing, you should identify whether the zero would also be considered a significant figure or not. And finally, once you've done those two steps, you should say the total number of sig figs in each of these values. First value is going to be 4,056. The second value is going to be 0,182. Third value is going to be 56,290. Then we'll go to 26.101, and then 0.0019, followed by 0.703, and finally 0.620. So take a second and do those two steps. First, identify if it's a leading zero, a middle zero, or a trailing zero. Second, identify if that zero is significant or not. Finally, determine the number of significant figures in each of these values. In 4,056, or 4056, the zero is between the 4 and 5. That makes it a middle zero, and middle zeros are always significant. So that has 4 significant figures. 0182, that zero's before any other numbers, so that's a leading zero, which means it's never significant. So that has 3 significant figures. 56290, that zero comes after all of the other numbers. That makes it a trailing zero. These are the annoying ones. Trailing zeros are sometimes significant. When we look at that number, there's a decimal point there. There's a decimal point after the zero, because that's what makes it the ones place. But it's not drawn. There's not a decimal place visible. And since there's no decimal place visible, that means that trailing zero is not significant. So this only has 4 significant figures. 26.101, that zero is between two ones. That makes it a middle zero, which is always significant. So this has 5 significant figures. 0.0019, those zeros are leading zeros. They come before the first number, which are never significant. It's true, there's a visible decimal point, but a decimal point being visible only affects trailing zeros. It only affects zeros that are following the rest of the numbers, and these zeros are leading the numbers, and leading zeros are never significant. So this is 2 significant figures. 0.703 actually has 2 zeros. There's a zero here, and that zero is before any other numbers, which makes it leading, and there's a zero here. That zero is between two other numbers, which makes it a middle or sandwich zero, which the leading zero is not a significant figure. The sandwich zero is a significant figure, so this one has 3 significant figures. And the last one, 0.620, this zero is before any other number, so it's a leading zero. This zero's after all the other numbers, so it's a trailing zero. Leading zeros never count, so the first zero is not a significant figure. But there's that pesky trailing zero. And a trailing or following zero, or a zero after all of the other numbers, and since we see the decimal point drawn, that means this is significant, so it's included, which is why this also has 3 significant figures. Hopefully it makes some sense why we use significant figures, And hopefully now you can understand when you see a measured value how many significant figures there are in it. Perhaps you already knew that before this lesson, but it's still important that all students coming into this class understand these basic principles about significant figures.